In Linux, we also have special permissions. What if I want a user to be able to do something that requires root privileges, but I don't want to give them these privileges? What's the use case for this? Glad you asked. There are certain commands that need to change files that are owned by root. Normally, if you need to change a file owned by root, you would have to use sudo. But we want to be able to have normal users change these files without giving them root access. Let's check out an example. Let's say I want to change my password. I would use the password command like we've learned. Pretty simple, right? Now I just enter in my new password, and my password is changed. We know that the password command secretly scrambles up our passwords, then adds them to this etc shadow file. Let's dive a little deeper into this file. Oh, it says this file is owned by root. How are we able to write our scrambled passwords in this file if it's owned by root? Well, thanks to a special permission bit known as setUID, we can enable files to be run by the permissions of the owner of the file. In this case, when you run the password command, it's being run as root. Let's verify this. We see the permissions on this file look a little odd. There's an S here where the X should be. The S stands for setUID. When the S is substituted where a regular bit would be, it allows us to run the file with the permissions of the owner of the file. To enable the setUID bit, you can do it symbolically or numerically. The symbolic format uses an S, while the numerical format uses a 4, which you prepend to the rest of the permissions like this. Similar to setUID, you can run a file using group permissions with setGID or setGroupID. This allows you to run a file as a member of the file group. Aha! Under our group permissions, we can see that the setGID bit was enabled, meaning that when this program is run, it's run as the group TTY. To enable the setGID bit, you can do something similar to setUID. The only difference is the numerical format uses a 2, so I can do something like this. Or something like this. There's one last special permission bit we should cover, and that's the sticky bit. This bit sticks a file or folder down. It makes it so anyone can write to a file or folder, but they can't actually delete anything. Only the owner or root can delete anything. Let's look at permissions for a /temp directory, where a lot of programs write temporary files to, and you'll see what I mean. I added the D flag to show information just for the directory and not the contents, but as you can see, there's a special permission bit at the end here, T. This means everyone can add and modify files in the /temp directory, but only root or the owner can delete the /temp directory. You can also enable the sticky bit using a numerical or symbolic format. The symbolic bit is a T and the numerical bit is a 1. So sudo chmod plus T my folder, or sudo chmod 1755 my folder works. So let's verify. Phew, that was a lot of information on special bits. You usually won't have to deal with these permission bits in a practical day-to-day manner, but it's important to know they exist in case you ever want to allow users to either share folders or even run commands with escalated privileges. User access, group access, passwords, and permissions are all core concepts in security. Right now, you're only working with permissions and access on a single computer scale. Eventually, you'll learn about access on multi-user levels across different networks and more in the next course on System Administration and IT Infrastructure Services. For now, congratulations! You've just taken your first step toward building a foundation of computer security knowledge. In the next module, we're going to switch gears and talk about our OS and how it manages software. Next, we've got 2 assessments for you covering Windows and Bash permissions. Once you're finished, you're granted permission to take a break before we hit the ground running in the next module.